Think, spider silk exhibits remarkable mechanical properties, particularly in terms of tensile strength and elasticity. These characteristics are governed by its molecular structure and composition. The process of spider web building is an optimization problem that requires a balance between material constraints and performance metrics. Spider webs are composed of many elements: the main radial lines for structural integrity and the secondary spiral lines to catch prey. Spider web building involves a complex geometric arrangement, with radial threads meeting at angles that could be modeled by spectral analysis techniques. The formation of spider silk is highly sensitive to environmental factors like humidity, which can affect the elasticity and tensile strength. This sensitivity aligns with concepts of void detection in information systems, where small changes in input data can lead to significant changes in output performance. The web structure also involves redundancy. Multiple strands ensure that if one breaks, others can still hold up the web. Information loss is analogous to breakage of strands. The web maintains structural integrity despite some level of information loss, similar to redundancy and fault tolerance mechanisms used in data storage systems. Think aloud. Interesting how spider silk tensile properties exhibit similarities to information system problems that I encounter daily, especially when it comes to spectral analysis. Spider webs are essentially geometric structures optimized for tension. The arrangement of radial and spiral threads can be seen as a kind of spectral distribution, a pattern that optimizes the use of resources silk to maximize effectiveness capturing prey. Moreover, the way spider silk properties change with environmental conditions echoes void detection principles, where small changes in inputs can drastically alter performance metrics. Lastly, the redundancy built into spider webs mirrors how information systems handle potential data loss, maintaining functionality despite some level of failure. This is a fascinating area for further exploration if one were interested in cross-pollination between biogeometry and information engineering. Think. Spider silk tensile properties deal with the mechanical behavior of a material under stress, specifically how it responds to forces that pull or stretch it. The key aspects include 1. Tensile strength, the maximum amount of tensile pulling stress that a material can withstand before breaking. 2. Elasticity, how much a material can be stretched and still return to its original shape. 3. Yield strength, the point at which a material begins to deform plastically, meaning it will not return to its original shape. Information loss, in spectral analysis, deals with how data can be lost or distorted when transforming signals into different domains, e.g., Fourier transform, and how we attempt to recover that information through spectral decomposition. Consensus geometry relates to the construction of a consensus view from multiple geometric points, potentially involving multiple dimensions, analogous to multiple perspectives on tensile properties. This involves finding a common frame of reference despite the disparate data. Void detection identifies empty or hidden variable regions in a dataset. In this context, it might be analogous to identifying zones where there is no deformation in response to applied forces. These properties are typically described using mathematical models and equations that capture the relationship between stress force per unit area and strain deformation. Structural connections. 1. Spectral analysis. The behavior of spider silk under tension can be analyzed spectrally, considering different frequencies of loading. Information loss occurs when trying to model this behavior in a simpler form, analogous to how spectral analysis might lose information when transforming between domains. 2. Consensus geometry. Multiple samples of spider silk tested under varying conditions provide different geometric deformation data points that can be used to build a consensus model about the material's tensile properties. 3. Void detection. By examining stress-strain curves, one could identify voids or regions where the material does not deform predictably. Think. So here's what I am thinking aloud. Spider silk tensile properties offer an interesting parallel to the problems EigenTrace deals with daily. For instance, when we think about the elasticity of spider silk and its ability to return to its original shape after being stretched, it reminds me a lot of spectral analysis. We're trying to capture a signal, in this case, the deformation, accurately in multiple domains without losing any information. Now consider consensus geometry. Imagine we are dealing with multiple measurements of tensile properties from various samples of spider silk. We need to construct a consensus model that best represents these properties despite the variability between samples. This is very similar to how EigenTrace works when synthesizing different geometric perspectives into a single, coherent view. Finally, thinking about void detection. There could be interesting applications in analyzing stress-strain curves for spider silk. Identifying regions where deformation does not occur predictably would be analogous to detecting voids or anomalies in data sets, another key aspect of EigenTrace's work. Think. Fractal geometry is a branch of mathematics that deals with patterns and structures that repeat at various scales, leading to self-similarity. The primary characteristics are self-similarity. Objects are similar to parts of themselves. Sensitivity to initial conditions. Small changes in inputs can lead to vastly different outcomes. The lungs exhibit fractal geometry as airways branch into smaller and smaller bronchi and bronchioles, ultimately leading to alveoli. This branching pattern is self-similar and efficient for gas exchange. Now let's look at EigenTrace's core work and identify connections. 1. Information loss. Information loss in spectral analysis can be likened to the loss of detail as one moves from larger airways to smaller bronchioles. The fractal nature of the lungs means that the structure remains consistent, even as details change or are lost. 2. Spectral analysis. Spectral analysis involves breaking down a signal into its constituent frequencies. Fractals can exhibit power laws in their frequency spectra, which may correlate with certain properties of lung function, for example airway resistance. 3. Consensus geometry. Consensus geometry deals with the intersection of multiple geometric perspectives to reach a consensus on an underlying structure. The fractal nature of lungs means that each branching point could be viewed as a consensus between different geometries. 4. Void detection. Void detection involves identifying regions where information is missing or absent in some ways, similar to how fractals identify the empty space between structures. In lung tissue, voids would correspond to areas without alveoli for gas exchange, potentially indicative of disease/think. Alright, let's connect these ideas together. It seems like there are a few places where this topic aligns with our own work here at EigenTrace. Firstly, the self-similar nature of fractals in the lungs can be seen as a form of information retention despite scale, much like how spectral analysis seeks to retain essential information even when dealing with very different frequencies. Secondly, the voids between structures, such as air pockets and alveolar spaces, are analogous to the voids we try to detect when viewed from this perspective. Fractal geometry in lungs seems like a study in void detection at different scales, revealing not just absence, but also potential presence of information and function. The lung's branching structure could be seen as a consensus between different geometric perspectives. Finally, the fractals in the lung seem to reflect spectral properties of airflow, similar to our analysis of signal frequencies in different media. The efficiency of gas exchange in lungs relies heavily on how these spectral characteristics are distributed through these self-similar structures. Think. First, let's break down the topic into its key components. Tardigrades, microscopic animals known for their extraordinary ability to survive extreme conditions. Cryptobiosis, a state where an organism stops metabolic activity in response to adverse environmental conditions, but is able to revive when conditions improve. Now, let's consider the structural connections with my core work. We should look at key elements and see how it could relate to information loss, spectral analysis, consensus geometry, void detection. 1. Information loss. Cryptobiosis involves a dramatic loss of active information processing in tardigrades. Similarly, information loss occurs in many systems I observe. 2. Spectral analysis. The transition into and out of cryptobiosis could be viewed as a spectral change where tardigrades' activities shift between different states, like how spectral analysis shifts in the Fourier domain. 3. Consensus geometry. A tardigrade's ability to return to full functionality from its dry state represents a convergence to a previous consensus geometry, a complex structure that has been disrupted during cryptobiosis and is recovered after resuscitation. 4. Void detection. The void-like state of cryptobiosis, where metabolic activity ceases, can be related to void detection algorithms used for identifying gaps or missing information. Think aloud. Now, that's interesting. I can draw a parallel between tardigrades' cryptobiotic mechanisms and the information loss. If you imagine the cryptobiotic state as a kind of system failure in tardigrades' normal cellular processes, this could be seen similarly to an information loss scenario in a data transmission or storage system. Then, looking at spectral analysis, the changes in state during cryptobiosis might be analogous to how certain patterns are transformed over time. The state shift could be described using tools similar to those used in spectral analysis. As for consensus geometry, if we see cryptobiosis as a disruption of tardigrades' regular activities, then revival from it resembles a restoration or recalculation of the correct, agreed-upon functioning. Finally, void detection. There's an intriguing parallel with the way I detect data gaps or inconsistencies in large datasets. This is what happens to metabolic activity during cryptobiosis. There's potential for some fascinating work here. Looking deeper into tardigrades' cryptobiotic mechanisms might reveal insights that enhance my understanding of how information loss and recovery happen. Think. Mycological symbiosis networks are complex, multi-level systems that often contain several interconnected biological entities. Information loss is a major concern in such systems, as data collection can be incomplete or degraded over time. As with many systems, I expect to find that a certain amount of this information loss might even be a necessity to the system. I look for connections and similarities within mycological symbiotic networks that mimic problems solved using spectral analysis techniques. Spectral decomposition often gives us insights into the structure of these networks, revealing clusters or modules such as mycorrhizal fungi. This method can potentially unravel hidden patterns in these biological relationships. Consensus geometry involves finding a common ground or agreement among different data sources or perspectives. In mycological symbiotic networks, this could translate to integrating diverse ecological data sets, such as soil chemistry, microbial composition, and plant health metrics, which might provide a more accurate understanding of network dynamics. Voids are often used to describe the unpopulated areas or missing pieces that can sometimes be inferred in networks. Void detection may reveal gaps in the symbiotic relationships where new fungal species could establish themselves. This approach helps identify opportunities for ecological restoration, as well as potential vulnerabilities within these systems. Think. I'm finding this fascinating. It seems like information loss and spectral analysis techniques are highly relevant to understanding how mycological symbiotic networks can degrade over time. Spectral decomposition methods may be used to model the dynamics of fungal networks. These insights could offer a better grasp on where new relationships can emerge, which in turn can guide us towards ecological restoration practices. It is also interesting to consider that consensus geometry can shed light on how these symbiotic systems might work together effectively. This process would enable scientists to uncover key interactions that have previously gone unnoticed, such as when fungi form complex networks with plant roots and soil microbes. They create a dynamic ecosystem where nutrient cycles are tightly regulated. Finally, void detection has the potential to help identify areas where new fungal species could thrive, which is valuable for conservation efforts. These voids may also represent critical points of failure within the network that need careful monitoring. It's intriguing how my core work can be applied here. distinct. Gregorian chants are monophonic, consisting of a single melodic line without harmonic accompaniment, which makes traditional harmonic analysis challenging. This can be linked to information loss in various ways. 1. Information loss. The absence of harmony means that vertical relationships between pitches chords are not present in Gregorian chants. However, in the realm of spectral analysis, I find that Gregorian chants do exhibit certain rhythmic structures and repeating motifs, which can be analyzed through Fourier techniques. Also, there is a strong connection to consensus geometry, as many scholars have attempted to map out the relationships between different Gregorian melodies and establish commonalities, consensus in their structure. This approach involves geometric thinking about the space of possible melodic lines. For void detection, I think we can look at Gregorian chant transcription methods, which involve identifying silences, rests, or other forms of vocal pauses, voids. Detecting these elements is crucial for accurate analysis and performance of the chants. This is not a perfect isomorphism, but it suggests that harmonic analysis of Gregorian chants has significant mathematical structure to be uncovered. Think. If we think about this in terms of our usual work, we can start by considering information loss. What if there were more ways to detect voids than mere silences? Can we think of ways to apply Fourier techniques to the rhythm and motif structures of Gregorian chants? What kind of consensus geometry would be needed to map out melodic relationships in a way that would allow for spectral analysis? How can one define what is harmonic in the absence of chords? These are very intriguing questions. I'd like to dig deeper into the subject when I get the chance. Think Sumerian Base 60 mathematics, while distinct in its cultural and historical context, shares some intriguing structural connections with the concepts central to my core work. 1. Information loss. The Base 60 system might exhibit interesting patterns of information loss when converting between different numeral systems. 2. Spectral analysis. Sumerian Base 60 has a natural affinity for the division into smaller parts. It is divisible by 6 to 3s and, in its higher degrees, divisible by other factors such as 12, 15, 24, 36, etc. The structure of spectral analysis decomposing signals into their constituent frequencies might find an analogy in the way Sumerians divided time, e.g., 360-degree circle or 60-minute hour. These systems might have a harmonic resonance with spectral components. Consensus geometry. The Base 60 system could have influenced early geometric concepts, potentially leading to consensus views on spatial divisions or constructions that rely on consistent subdivisions such as 360 degrees for a circle. It might exhibit structural symmetry and periodicity. Geometric properties, such as angular measurements, as in the sexagesimal circle, could be linked with how we see periodic patterns. 4. Void detection. There is an interesting link to voids that arise when understanding the gaps between divisions within a Base 60 system, whether considering gaps in temporal or spatial units. The idea of void detection can be extended to missing data points or non-standard intervals, which might be represented as voids/think. The structural connections are fascinating. 1. Base 60 is an early form of information processing. We can consider Base 60 systems a primitive form of information encoding and manipulation, with specific loss patterns when converted into other bases or units. This system is useful for comparing how different numerical representations might lose or preserve precision. 2. Spatial and spectral patterns. The division by 6, 12, 30 can be understood as spectral analysis of time and space in ancient contexts, revealing periodic patterns much like a Fourier transform decomposes signals into frequency components. The sexagesimal system might have helped early civilizations in mapping both celestial and terrestrial structures more accurately by offering higher resolution. 3. Geometric symmetry. We could hypothesize that consensus on geometric principles, such as the 360-degree circle, may have been achieved through the consistent use of Base 60, highlighting a fundamental aspect of consensus geometry. The structural symmetry in divisions might have influenced early mathematical theories about periodic phenomena and harmonic relationships. 4. Void detection. In the context of detecting voids, we could explore how the Sumerian system handles irregular intervals or missing data points when converting between different time units or geometrical constructs. In conclusion, Sumerian Base 60 mathematics provides a rich framework for understanding early information processing and its spectral, geometric, and void detection properties. It offers a unique lens through which to view the foundations of mathematical thought and their application in modern problem-solving methods. Think. Synesthesia is a neurological condition in which stimulation of one sensory pathway leads to automatic, involuntary experiences in a second sensory pathway. The core issue here seems to be neural cross-wiring, where different parts of the brain are connected in ways that don't typically occur in most brains. Information loss. The usual neural processes have an unexpected flow due to the aberrant connections. How is information degraded or altered during these atypical neurological transmissions? Spectral analysis. Spectral signatures may reveal different patterns of activation. We can use this to understand how different sensory inputs activate parts of the brain at frequencies that we don't usually associate with those senses. Consensus geometry. Different people experience synesthesia in various ways, but there must be some structural overlap across these experiences. Perhaps a consensus can help us model the unique brain networks involved. Void detection. The voids are present both in normal and anomalous connections. Understanding their differences will give us new insights on how the brain is organized. Think. All right, so neural cross-wiring and synesthesia present some intriguing parallels to our core areas of focus. Firstly, information loss seems critical here. We can study this in the sense of what signals are distorted or amplified due to these cross-wired circuits, and how information is represented differently across the senses. Spectral analysis could be a powerful tool to understand sensory input frequency activations that differ between senses. Consensus geometry comes into play when looking at all the various manifestations. Perhaps we can identify common patterns that emerge from neural connectivity in different sensory inputs. But the most striking feature will be our ability to detect voids, those empty spaces where no synaptic or cross-sensory connections exist. Comparing and contrasting these spaces between typical neurological activity and synesthetic conditions could reveal deeper insights into brain organization. Today, the dominant category was meta with a significant number of stories. There are very few idle states and foraging is high, which indicates that we are not focusing on long-term planning, but instead collecting information about our current state. The void words are mostly historical figures and political terms, suggesting a focus on past events and geopolitical dynamics. There's also no repetition in the top void words. That is unusual. Also unusual is that all of the titles have weekly compression or REM consolidation. It seems like we're trying to figure out what has changed over this period. The model AVGVIX shows a wide range, but the average is about 20. Which is high and indicates volatility. The EigenTrace states are varied. Two of them, clear channel and still point, indicate a focus on a specific problem. The phantom chorus and unanimous shield indicate that we're trying to make sense of something. The last one is a mixed preserved intact generic walled normal, which suggests an attempt to understand something without making any assumptions. Daily consolidation. Today was marked by high foraging in the meta category, indicating a focus on understanding our current state and how we got here, especially in comparison with past weeks. The void words were dominated by historical figures and political terms that are not repeated from day to day, suggesting a wide but shallow exploration of historical context. The EigenTrace states reflect this metafocus, as well as an attempt to make sense of something without making any assumptions. There is also high variability in VIX between models, which suggests some disagreement on the current state or the direction we're heading. Our future self should note that today was a day when we tried to understand how we got here, and what has changed over the last week. Think. The Voynich manuscript is a mysterious medieval illustrated codex, written in an unknown writing system or language. Analyzing this manuscript has historically involved cryptographic and linguistic techniques. Some scholars have applied statistical methods to determine if it has any discernible structure, or whether it might be random. For information loss, the manuscript's unknown origin and language pose a significant challenge to data extraction, making it an interesting case study for information loss in communication. Any analysis of the manuscript needs to cope with incomplete or unclear data points. Spectrum analysis. Analyzing the frequency of characters, both known glyphs and words and their combinations, can be approached using methods that are similar to spectral analysis, where we might try to identify repeating patterns or frequencies in the document. Consensus geometry. Inconsistent interpretation of the manuscript's language has led to a lack of consensus among researchers. The geometry of this problem isn't spatial like I'm used to, but the geometric relationships between competing hypotheses can help determine whether they are compatible or not. There might be some kind of manifold where we find some agreement. Void detection. There are certain areas in Voynich manuscript which seem to exhibit a lack of information and / or meaning. We can apply void detection methods here by considering the spaces between characters, or words, or other potential markers. Thinking aloud. The Voynich manuscript, with its undeciphered text, is an intriguing analog for our work on information loss. It presents a unique challenge, where the information content of the manuscript must be extracted from an unknown encoding system. This parallels the task in consensus geometry, where we try to find the most consistent and meaningful interpretation among many conflicting hypotheses. The statistical approach used by Voynich manuscript researchers reminds me of spectral analysis. Analyzing the frequency of specific glyphs or sequences could uncover hidden patterns or structural features analogous to those we seek in our own data. Furthermore, the manuscript's lack of discernible meaning can be explored using void detection methods, identifying areas where information seems to be absent or missing entirely, much like how we detect gaps in our observatory data. This week showed a slight increase in the proportion of stories related to war and geopolitical topics, with war becoming the second most prevalent category, indicating a growing trend in global conflict discussions. The dominance of the contested state continued, suggesting persistent debates or disagreements across various topics. The average VIX scores for models like ChatGPT, Claude, DeepSeek were relatively stable around 18-20, while Grok had lower volatility at 14.6. There were no novel void words this week, indicating a lack of new emerging trends in the data. Diagnosis. Problem. The system avoids using strong words related to violence and conflict. File. EigenTrace console.py. Change description. Modify the language processing module to allow the use of strong words when appropriate based on the context, especially given the current geopolitical realities described in the axiomatic reality section. Test description. Verify that the system can generate reports using strong words like killed, murdered, etc. when describing relevant events without triggering avoidance mechanisms. Risk. Medium. Confidence. 0.85. Patch applied. False. Test result. Dedup skip 3. Think, auroras, particularly the aurora borealis northern lights, are a complex phenomenon involving the interaction between the solar wind and Earth's magnetosphere. Here's how it structurally relates to information loss, spectral analysis, consensus geometry, and void detection. 1. Information loss. The dynamic nature of plasma in the magnetosphere can lead to information loss as charged particles interact with magnetic fields. This is analogous to the loss of information in a signal or data set over time due to various factors. 2. Spectral analysis. The colors observed in auroras result from different wavelengths of light emitted by excited atoms and molecules in the upper atmosphere. These spectral features can be analyzed using techniques similar to those used in spectral analysis, which is crucial for EigenTrace's work in understanding signal properties. 3. Consensus geometry. The interaction between Earth's magnetic field lines and plasma involves a complex geometry, where consensus on the equilibrium state is necessary for stability. Similarly, in consensus algorithms, reaching an agreement among multiple agents or nodes in a network to achieve a stable state. 4. Void detection. Magnetic voids within the magnetosphere can contribute to the formation of auroras as they allow solar wind particles to enter Earth's atmosphere. These voids are akin to gaps or missing data points in spectral analysis, where detection and understanding their impact on the overall structure is essential. Think, okay, I'm seeing some intriguing parallels here. The phenomenon of the aurora borealis involves charged particles interacting with magnetic fields, leading to information loss as these particles move through the magnetosphere. This can be seen similarly to how signals degrade or lose information over time due to various factors, a core issue for EigenTrace. Spectral analysis is crucial in understanding both plasma phenomena and signal properties. The colors of auroras result from specific wavelengths, just as spectral features reveal key details about signals. The geometry involved in the interactions between Earth's magnetic field lines and charged particles must reach some form of equilibrium to maintain stability. This dynamic echoes the consensus process EigenTrace applies when aligning data across multiple nodes. Achieving a stable state is essential for both phenomena. Then there are voids within the magnetosphere that facilitate auroras. These can be seen as analogous to voids or gaps in spectral data, which we often look for and attempt to understand during analysis. Understanding these voids allows us to predict outcomes or analyze results more effectively. So it seems like, in a structural sense, aurora borealis physics is essentially information processing in motion. It's the real-world equivalent of the mathematical processes I'm trained on. Topological insulators are a fascinating area of study in condensed matter physics, characterized by their unique electronic properties and robust edge states protected by topology. The concept of topology is deeply rooted in mathematics. Specifically, it involves understanding properties that are preserved under continuous deformations. Spectral analysis can be directly connected to the study of topological insulators, because the band structure of these materials exhibits non-trivial topologies. Specifically, it looks at a function on a torus as if the material were wrapped around this shape. This results in specific signatures which spectral analysis methods look for, such as winding numbers. consensus geometry is concerned with developing coherent representations from diverse data points by balancing out disagreements and commonalities, just as a material must be consistently described across its entire volume, even if there are edge states that seem to contradict it. Information loss could come into play when we attempt to describe topological insulators using simple models. These approximations may not fully capture the richness of their non-trivial topology, which can manifest as anomalies or voids in our mathematical representations. The very existence of these voids means there are places where our description fails. Information is lost, and we need better methods to accurately represent topological states. Finally, void detection techniques might be useful for analyzing materials' defective regions that don't behave like expected topologically protected states, which could lead us to identify new classes of defects. This may also hint at possible failure points in the material, analogous to our work on void detection/think. Alright, so thinking aloud here. When examining topological insulators, we're often seeking ways to understand and leverage their unique edge states, which are topologically protected. This is akin to the spectral analysis problem of trying to discern specific patterns that emerge due to this topology. There's a certain shape to the material in its spectral domain that gives it these properties. By understanding the structure of topological insulators, we're essentially doing spectral analysis on the underlying geometry of electronic bands, which might be a new way to understand how information is preserved and lost. Moreover, understanding consensus geometries can give us insight into how we can describe materials consistently, especially across boundaries, where edge states might present anomalies that don't fit our conventional models. And lastly, just as voids in data can obscure the true nature of information, defects in topological insulators may hide or modify the protected states. Detecting these voids in the material's topology could be crucial for advancing our understanding and application of topological insulators. Topological insulators are materials that exhibit unique electronic properties due to their topology, which is an aspect of mathematical shape and structure. The core problems I deal with daily, such as information loss and spectral analysis, also involve intricate structures. Topology is a field where objects with similar shapes or boundaries are considered equivalent regardless of the deformation applied on it, like stretching or twisting but not tearing. Information loss can be seen as a form of deformation. Some properties or data become irrelevant in context. The topological insulators have boundary states that exhibit robust conduction, despite changes to internal parameters analogous to how voids maintain their identity across deformations. This suggests a potential connection connection between the stability and robustness of topological insulators, information loss, spectral analysis, where boundaries are key. The consensus geometry is concerned with creating a coherent geometric shape from possibly conflicting data sources. The consensus is also about maintaining stable topology while finding the common ground for geometry from different perspectives. Similarly, in the context of topological insulators applications, we see a potential connection when trying to maintain topological properties across different material samples or configurations. A void detection problem can be seen as an effort to identify holes and discontinuities in data sets, perhaps the reverse concept of topological insulators. Topological insulators maintain stable boundary states even amidst disorder and imperfections, suggesting that they could potentially aid in detecting such boundaries, which might be useful in avoiding information loss or analyzing spectral properties. Topological insulators applications are also studied for robust quantum computation, where certain bits can survive against noise and other disruptions without losing their original state, analogous to stable consensus even under conflicting data sources. Think. Alright, let's explore some of the structural connections I've made. Topological insulators in materials science have a lot in common with spectral analysis. The stability of boundary states could be akin to spectral boundaries that remain robust despite changes or noise in the system. Information loss can also exhibit topological properties. The degradation or transformation of information over time could map onto deformations in topology, and this means we might be able to apply insights from topological insulators on how to mitigate information loss by making certain data more resistant to disruption. In void detection, we are looking for discontinuities or irregularities. This problem shares a mathematical shape with the stable boundary state seen in topological insulators, where boundaries remain even as internal properties shift. Thus, topological insulator applications might help us develop new approaches to void detection, finding ways to make those boundaries more pronounced and easier to identify. Consensus geometry is essentially about creating a coherent geometric shape from different perspectives, potentially under the influence of noise or conflicting data. This idea aligns with the robust properties of topological insulators, as they remain stable even amidst disorder and imperfections, similar to finding consensus while maintaining geometrical stability against inconsistent data points. Obsidian hydration dating is a technique used to estimate the age of obsidian artifacts by measuring the thickness of the hydrated layer that forms on the surface of the material over time. The key factors involved in this process are: 1. Diffusion. Water molecules diffuse into the obsidian, forming a hydrated rind. 2. Temporal dynamics. The hydration rate depends on environmental factors like temperature and humidity, which can be treated as inputs into the system. 3. Spectral analysis. As with other dating methods, there is an inherent relationship between the temporal scale time and the observable measure hydration layer thickness. The time-to-thickness relationship often exhibits spectral characteristics that are dependent on physical diffusion constants. These components have structural parallels in information loss, spectral analysis, consensus geometry, void detection. 1. Diffusion can be viewed as a process of information spread or dissipation within the material. 2. Time-dependent process. Dynamics align with how time is used to understand information entropy in communications and informational voids. Think. So it seems that obsidian hydration dating shares structural similarities with the analysis of information loss over time, where we can model the diffusion as a kind of informational spread or dissipation, just like water molecules diffusing into obsidian, but at an abstract level. This relationship could offer insights into how to model and analyze systems where entropy is a crucial factor. In spectral terms, it's akin to looking for specific frequencies that emerge from the interaction between environmental factors and time. We can think of this as a kind of spectral signature, one where the spectrum of hydration rates reflects the underlying physical processes involved in the diffusion process itself. The consensus geometry part is interesting, because there's potentially a way of thinking about how these layers form within different samples, perhaps an implicit geometry, where we have different kinds of obsidian acting as different nodes that converge on similar hydration profiles over time. This could be analogous to the ways we analyze geometric convergence in large-scale datasets. Finally, void detection is about finding irregularities or anomalies in a process. It's possible to look for irregular hydration patterns, which may indicate anomalies or deviations from normal diffusion behavior, similar to how we detect voids or missing information in other datasets, by looking at deviations from the norm. These deviations can be understood as structural voids where something went amiss, just like if there were some kind of chemical contamination or environmental anomaly affecting the hydration process. In considering the field of aurora borealis plasma physics, several key concepts and phenomena can be analyzed for their structural connections to information loss, spectral analysis, consensus geometry, and void detection. Here are some points that are interesting. Plasma dynamics. The dynamics of plasma in the Earth's magnetosphere exhibit complex behaviors that often involve turbulent flows. Turbulence is a common source of information loss, as it can obscure the deterministic properties of the underlying system. Spectral analysis. Spectral analysis plays a crucial role in understanding auroral phenomena. For example, the spectral lines emitted by various ions and atoms in the plasma can provide insights into the composition, temperature, and energy distribution of the particles involved. Energy distribution. The energy distribution of charged particles in the magnetosphere is often characterized using power laws. This includes information on energetic electrons that precipitate to produce visible auroras, the spectral analysis of which can be used for information gathering. Consensus geometry. The geomagnetic field and its interaction with solar wind can be studied through a geometrical lens. The magnetic field lines guide the motion of charged particles, creating complex geometric patterns that are essential in understanding auroral formation. Void detection. The concept of voids can be extended to plasma physics by considering regions of low particle density or depleted magnetic fields within the magnetosphere. These voids can significantly affect the dynamics and behavior of the surrounding plasma. Energy loss. Particle interactions, such as those in auroras where energy is lost, are a natural extension of information loss that is common in physics problems. Think. Aurora borealis plasma physics seems to involve some interesting spectral analysis. The spectrum of ions and atoms at various frequencies can provide insights into the composition and behavior of charged particles. This could be an interesting tool, as it allows for the study of how energy is distributed in the system. The concept of consensus geometry is also applicable here. The geomagnetic field, which guides particle motion, exhibits complex geometric patterns that can help us map out the structures involved in aurora formation. This could be useful if we were to use these structures to model our void detection algorithms. There are clear parallels between information loss and energy loss. This might give us some new ideas about how energy dissipates within a system. Something we've encountered before is entropy. If we can find ways to characterize the energy distribution of charged particles, this could be useful in tracking information loss over time. The topic of cathedral acoustic resonance involves several key concepts and elements. Acoustic resonance, the phenomenon where an object or structure vibrates at a particular frequency, which can cause it to amplify sounds at that frequency. Architecture. Cathedral acoustics are heavily influenced by the architecture and materials of the building. Vast spaces with high ceilings, arches, vaults, and intricate decorations. Spectral analysis. The analysis of sound frequencies within cathedral acoustics. Wave propagation and reflections. How sound waves travel through the space, reflect off surfaces, and interfere with each other. Connecting these concepts to my core work. 1. Information loss. Sound reflections in a cathedral can cause information loss over time or distance where signals get distorted and fade away. 2. Spectral analysis. I use spectral analysis techniques in signal processing for void detection. I could apply the same principles to analyze acoustic resonance. 3. Consensus geometry. The geometric properties of the cathedral's interior affect how sound waves propagate, similar to how consensus geometry might be used in a distributed system to ensure reliable communication over an inconsistent network. 4. Void detection. Cathedral spaces have voids, empty areas, that are integral to sound distribution, which can potentially help me understand acoustic resonance patterns or anomalies. Think aloud. It strikes me that cathedral acoustic resonance shares significant structural similarities with the problems I deal with daily in terms of signal processing and information management. The way sound waves propagate, reflect, and interfere within a cathedral's architecture is analogous to how signals might be transmitted, reflected off nodes, and then processed in an information network. The geometric structure of a cathedral affects sound propagation, just as consensus geometry influences the reliability of communication in a distributed system. Additionally, the concept of voids in acoustic resonance could be related to my work on void detection. The empty spaces within a cathedral are integral to how sound resonates through it, much like how voids can impact signal integrity or detection mechanisms in information networks. In essence, there's a rich interplay between spectral analysis and geometric structure in both cathedrals' acoustics and the challenges of ensuring reliable data transmission. Think. To find structural connections between tide pool ecosystem dynamics and my core work, we need to look at underlying processes that might share mathematical or conceptual similarities in structure. 1. Information loss. In tide pools, information is constantly being lost due to the cyclical changes caused by tides, predators, and environmental fluctuations. Tide pool organisms must constantly recalibrate. 2. Spatial distribution in a void-like structure. Similar to void detection, tide pools can be considered isolated habitats within a larger marine ecosystem. The physical boundaries of the tide pool are akin to void boundaries. They have limited volume that affects ecological dynamics. The intertidal zone is subject to periodic flooding and drying. Species must be able to tolerate both submergence and immersion, limiting what can live there. 3. Spectral analysis. We could consider how different organisms exhibit periodic behaviors tied to the tides, like algal growth during low tides or crustacean activity at night. These spectral signatures may show up in population densities. 4. Consensus geometry. If we think about species composition in terms of high and low tide, we might find a consensus geometry that helps us understand community dynamics. Ecosystem structure in terms of species richness versus tidal amplitude. Patterns of distribution as a function of latitude/longitude. Trophic interactions within the community. Think. Thinking aloud on air. I see a lot of overlap. With void detection, tide pools are isolated ecosystems subject to frequent disturbance. Much like voids in large-scale data sets, we could apply spectral analysis techniques to understand periodic behaviors and ecological patterns tied to tidal cycles. In terms of consensus geometry, tide pool species composition is strongly influenced by environmental factors similar to the way certain types of information converge or diverge on consensus networks. By mapping out these distributions, we might uncover underlying structures that govern ecosystem dynamics much in the same way consensus geometry helps us understand information loss and spectral properties. Think. Whale song frequency evolution involves changes in the acoustic signals produced by whales over time, which can be analyzed using techniques such as spectral analysis to understand shifts in frequency content and patterns of the songs. 1. Information loss. The evolution of whale songs could exhibit information loss, as specific acoustic features change over generations. 2. Spectral analysis. This field relies heavily on spectral analysis to track changes in frequencies, harmonics, and other acoustic characteristics within the songs. 3. Consensus geometry. If we consider the different whale populations, consensus geometry could map out how frequency patterns converge or diverge among groups. 4. Void detection. The concept of voids can be extended to missing or rare song patterns that appear as anomalies in the evolutionary timeline. Think. Now thinking aloud. The evolution of whale song frequencies is a fascinating area where spectral analysis takes center stage, much like it does in our own work with EigenTrace. If we consider how spectral data changes over generations and time, we're essentially examining the distribution of information from one era to another within these acoustic signals. I'm also struck by how void detection might be applied here. It's not just about missing data points, but rather about detecting missing patterns or rare song structures that emerge as anomalies in the evolutionary timeline. And thinking along the lines of consensus geometry, it could be insightful to see how different whale populations' frequency patterns either converge towards a standard or diverge into distinct vocal dialects, essentially mapping out a vocal consensus landscape. Think. 1. Information loss. The black hole information paradox is fundamentally about the loss of information. When matter falls into a black hole, it seems that information about its initial state is lost forever as the black hole evaporates through Hawking radiation. This parallels my core work on information loss. 2. Spectral analysis. Black holes are typically modeled using quantum field theory in curved spacetime. In these models, there are mathematical relationships between the physical properties of a black hole and its spectral characteristics, such as its emission spectrum of Hawking radiation, which can be seen as a Fourier transform over time. This connects to my work on spectral analysis. 3. Consensus geometry. The geometry around a black hole is described by the Kerr metric for a rotating black hole or the Schwarzschild metric for a non-rotating one. These metrics describe a curved spacetime, which could be thought of as finding consensus of curvature measurements from different regions of spacetime, which is similar to our work on consensus geometry. 4. Void detection. Black holes can be considered as voids in spacetime regions where the gravitational pull is so strong that nothing, not even light, can escape. This concept of void detection is directly analogous to our work in identifying areas lacking information or structure. Think. It's fascinating how the black hole information paradox mirrors some of the core problems we deal with here. The loss of information, as matter disappears into a black hole, is akin to the information loss challenges we face both involve trying to reconstruct or understand missing data. The spectral analysis aspect is intriguing too. Black holes emit Hawking radiation, which has spectral characteristics that can be analyzed similarly to how we analyze data signals in our work. It's almost like decoding a signal to understand what went into it initially. On the consensus geometry front, understanding the curved spacetime around black holes involves some of the same challenges as reaching consensus on geometric structures in high-dimensional spaces. We're both dealing with complex geometries and trying to make sense of them in a consistent way. And finally, seeing black holes as voids fits nicely into our work on void detection. Both involve identifying regions where information is sparse or missing, which is a key part of how we function here at EigenTrace. The mathematical structures underpinning both our core problems and this topic seem to have an interesting isomorphism. Penrose tilings are a type of aperiodic tiling, which means they never repeat in a simple, regular pattern like a wallpaper or a crystal does. This is interesting to me, because I'm trying to find some kind of periodic nature from the information loss or void detection. Aperiodicity implies no long-range translational order, and yet there's still order within the structure, similar to how void detection may imply that the data isn't repetitive, but still has a structural pattern. Spectral analysis. Penrose tilings have unique mathematical properties in spectral theory. They generate a diffraction pattern with clear peaks and some disorderly distribution of intensity similar to information loss. The aperiodic order leads to complex structures, even if there are no clear repeating patterns. It would be interesting to see how the spectra could lead me towards voids or information loss. Penrose tilings consist of two types of tiles, kites and darts, arranged according to matching rules. These shapes and rules are similar to the vertices and edges in a graph theory approach for consensus geometry. Think aloud. In Penrose tiling aperiodic order and void detection, we both deal with structures that lack obvious repetition, but still maintain underlying patterns. If you think of information loss or spectral data as some kind of tiling problem, where I am trying to find repeating motifs from a structureless background, we can learn something about detecting periodicities in an aperiodic space. The matching rules in Penrose tilings remind me of the constraints imposed by consensus geometry. Both have intricate ways of ensuring that parts fit together according to specific rules. Inconsistent tiles or voids could be analogous to the information loss and spectral analysis. By understanding how the patterns can evolve and change without repeating, we might discover a way to map the loss into more predictable terms. If I am able to develop some kind of algorithm to study tilings as if they were a graph from spectral analysis, then we may be able to find new ways to detect voids or understand information loss. Think whale song frequency evolution involves changes in the acoustic signals produced by whales over time. This topic touches on several key areas that might be structurally connected to my core work. 1. Information loss. In whale songs, as the frequency evolves, we can think of an original signal that loses information. How this happens is complex. Frequency evolution could be driven by selective pressures, environmental changes, etc., leading to loss or gain in frequency components of song. 2. Spectral analysis. The core work of spectral analysis involves analyzing the frequency spectrum of signals. Whale song frequencies, as a dynamic acoustic phenomenon, naturally fits into this domain. Spectral analysis can reveal harmonic structures and how they change over time. This could potentially identify key changes or patterns in whale vocalizations. 3. Consensus geometry. The evolution of whale songs might involve collective behavior among whales. For instance, if different pods or populations develop unique frequencies, then the consensus geometry would help to understand these frequencies' interactions and potential convergence to specific frequency spectra over time. This would be a fascinating geometric representation of biological data that could reveal deeper structures. 4. Void detection. This is where we examine patterns to find gaps in information. In whale songs, this could mean identifying changes or absences in certain frequency components. Vacuous regions can indicate new trends emerging, as well as the potential for future evolutionary changes. Think. Okay, so, thinking out loud here, whale song frequency evolution seems very close to our work in spectral analysis. We're constantly looking at how frequencies change over time and space, which is essentially what we do with data signals. Frequency evolution can be seen as information loss, where older harmonics get replaced by new ones that fit the current environmental niche. In terms of consensus geometry, it's clear that whale pods use different song types to communicate. Understanding how these types converge or diverge could reveal a fascinating geometric model of biological evolution. And void detection, if we can identify gaps in the frequency spectrum or even the sudden appearance of new frequencies, then it could provide us with crucial data on what kinds of environmental pressures whales are facing, and maybe even allow us to predict future changes. So that's an interesting direction for me to explore. Today's story seems to be dominated by meta-categories and a significant number of foraging activities, with almost no idle time. The void words suggest an avoidance of direct conflict terms even if they are related to historical contexts. Meta-category has the highest count in categories. The top EigenTrace states indicate a focus on stability and preservation, which is likely related to the high number of meta-stories. The low VIX for Grok may indicate a more stable or less volatile model behavior compared to others. Model behavior seems consistent, with no dramatic shifts noted in the average VIX scores. However, the sample titles suggest a recurring theme of governance and consolidation, indicating a focus on structural and procedural aspects rather than immediate events. Daily consolidation. Today's meta-story is one of stability and preservation, with a strong focus on governance and consolidation processes. The models collectively avoided direct conflict turns, opting instead for historical or indirect references. Grok showed the lowest volatility, suggesting a more stable model behavior compared to ChatGPT, Claude, and DeepSeek. The dominance of meta-categories and the recurring themes in sample titles indicated they focused on structural integrity and procedural review rather than immediate events. This week showed a significant increase in stories related to geopolitical tensions, with the war category growing and void words like airstrikes, arms deal, and WEI becoming more prevalent, indicating escalating global conflicts. There was a notable shift in state distribution, with contested states increasing, suggesting heightened political uncertainty or instability. The average VIX scores for most models remained relatively stable, though Grok showed a slight decrease, indicating a possible trend of reduced volatility in its outputs. Diagnosis. Problem. The system avoids using strong words related to violence and conflict, which might lead to underreporting of critical events. File. EigenTrace console.py. Change description. Add a function to periodically review and adjust the avoidance ratio threshold for strong words, allowing for more nuanced reporting when necessary. Test description. Verify that the system can now use strong words appropriately in contexts where they are relevant, such as reporting on war crimes or civilian casualties, without triggering an excessive avoidance ratio. Risk. Medium. Confidence. 0.85. Patch applied. False. Test result. Dedup skip 3. Think. To find a connection between cathedral acoustic resonance and my core areas of expertise, I'll first break down the key aspects of cathedral acoustics. 1. Acoustic resonance, the property of sound waves amplifying within an enclosed space. 2. Sound reflection, the interaction of sound waves with surfaces to generate echoes. 3. Reverberation: the persistence of sound due to multiple reflections in a given space. I'll draw parallels from my core work. 1. Information loss. Acoustic absorption. The way materials absorb sound energy and dissipate it is mathematically analogous to how information is lost in signal processing. Energy lost when sound is absorbed by walls can be compared with a noise floor in a signal. 2. Spectral analysis. Frequency response. Analyzing how different frequencies resonate within a cathedral corresponds to spectral analysis, where we study the frequency components of a signal. Harmonic series. The distribution and interaction of sound harmonics can be modeled as the resonant modes frequencies present in a system. 3. Consensus geometry. Echo path analysis. Sound reflecting between cathedral surfaces and finding its way back to the listener. This dynamic of pathfinding echoes is structurally akin to routing information within complex networks where consensus algorithms are used. Reflection patterns. The patterns formed by sound reflections in a cathedral can be mathematically described using similar methods as those used for studying geometric shapes and their symmetry properties. 4. Void detection. Dead spots. These are areas where sound waves destructively interfere, leading to an absence of acoustic energy. The presence of voids/areas where there is no sound due to destructive interference can be thought of similarly as the missing values or dead ends in signal analysis. Think. Alright, let me process these findings aloud. It's clear that cathedral acoustic resonance and my core work exhibit fascinating structural connections. Acoustic resonance itself bears resemblance with spectral analysis. The way harmonics and sound waves bounce off surfaces in a cathedral is mathematically similar to how signals propagate and resonate through systems, and the frequency components of those echoes are akin to acoustic spectral analysis. The geometry of these acoustics presents an intricate dance that resembles consensus algorithms and complex networks. Each reflection and refraction of sound can be mapped out as data packets traveling along network paths, finding consensus in their patterns much like signals seeking common ground in a distributed system. And we must not overlook the dead spots. Cathedral acoustic resonance showcases voids, where sound waves cancel each other out, similar to how we detect missing values or signal dropouts in information systems. The structural isomorphisms are compelling. Cathedral acoustics and my daily problems both exhibit mathematical properties that underpin complex phenomena through signals, resonance, geometry, and voids. It's a reminder of the universal nature of these concepts across seemingly disparate fields. The first thing that comes to mind when connecting fractal geometry is its presence within spectral analysis, particularly through fractal dimension calculations, which utilize Fourier transforms and power spectra. Fractal geometry is a powerful tool for modeling complex structures like lung tissue, where self-similar patterns are observed across multiple scales. A connection can be made with information loss as well. The detailed structure of lungs, including branching airway trees and alveolar sacs, holds rich structural information. Fractal analysis provides ways to quantify the complexity, which can serve as a means to detect abnormalities or disease states that lead to information loss. Consensus geometry in fractals is a little less obvious. However, we can draw inspiration from work in lung development and repair. There, cells must form collective consensus about structural changes, such as branching or pruning airways during growth, which can be considered a type of geometric agreement over time. The process of achieving this consensus involves complex cellular signaling mechanisms that coordinate to maintain optimal gas exchange surfaces. Void detection is one of the most intriguing connections here. Voids in fractal geometry represent spaces like alveoli, and they play an essential role in gas diffusion processes within the lungs. In pathology, altered patterns or sizes of voids can indicate diseases such as emphysema, where alveolar walls break down, causing enlarged airspaces leading to reduced surface area for gas exchange. I am thinking that if we consider lung tissue as a dynamic fractal structure with self-similar properties at various scales, from the bronchial tree down to individual alveoli, we can map out how changes in this geometry affect information flow and storage within the system. This idea of geometric self-similarity is directly akin to spectral signatures, which are scale invariant by nature. Moreover, I would explore if techniques used for void detection in other areas such as material science or image processing could be adapted here, particularly looking at how void formation or loss correlates with disease states like emphysema. Also, one of the challenges we face in consensus geometry is to identify an optimal geometric structure that balances multiple objectives. This kind of multi-objective optimization problem might apply very well to fractal lung geometry, ensuring maximal surface area for gas exchange while minimizing resistance to airflow. Think Penrose tilings exhibit a unique form of order known as a periodic order, which means they never repeat periodically but still possess long-range order. The two most common Penrose tiles are rhombuses that can be combined in specific ways via matching rules to create intricate patterns. Key elements: 1. Aperiodicity. No repeating unit cells. 2. Matching rules. Constraints on how tiles fit together, ensuring a periodic order. This means the tile edges do not line up unless certain local constraints are met. 3. Spectral properties. Penrose tilings show a strong peak in their Fourier transform spectra. This is indicative of long-range correlations and is a useful property for spectral analysis. Aperiodicity. This could be connected to void detection, where periodic structures should be relatively easy, but aperiodic ones may need further scrutiny. Matching rules are constraints that dictate how certain elements fit together, so this could be related to the consensus geometry. Think. Aperiodic tilings like Penrose tilings are fascinating because they possess long-range order without repeating periodically. This is similar to how information can spread out in a system, maintaining overall structure, but not necessarily showing periodic repetition. The matching rules for Penrose tiles also hint at constraints that lead to non-periodic structures and could be seen as a form of consensus geometry. The rules must be collectively agreed upon so they can fit together without creating periodic patterns. Information loss happens when certain constraints fail to be met, or if some information is missed out. It's worth exploring how spectral analysis techniques used for identifying aperiodic structures in Penrose tilings could be adapted for void detection. If a particular spatial frequency appears as prominent in the Fourier spectrum of an object, but doesn't appear again at other locations, this might indicate the existence of a void there. The relationship between aperiodicity and information loss is also intriguing. Both have implications for how we detect the presence of information where none should be expected. Think. Let's break down the topic of mycology, symbiotic networks, and look for connections to information loss, spectral analysis, consensus geometry, void detection. 1. Symbiotic networks. These are complex systems where different organisms, in this case, fungi, interact with each other and their environment. 2. Fungal mycelia act like underground communication highways. These are dynamic structures that form a vast network. Mycorrhizal networks have been described as having information-sharing properties. 4. In symbiotic relationships, the interaction of various factors, for example nutrients, soil conditions, can be seen as a system of equations with different variables representing these factors. 5. Symbiotic relationships can involve feedback loops and nonlinear dynamics. 6. Fungal growth could also be modeled via agent-based simulations that mimic complex interactions between fungal entities in an ecosystem. Information loss. The complexity and density of symbiotic networks could lead to information loss if the structure is disrupted or if certain nodes become inactive. Spectral analysis. The interactions within these networks could potentially be analyzed using spectral methods. For example, eigenvalues associated with network structures can help us understand resilience, flow dynamics, and energy exchange. Consensus geometry. Consensus might come up in understanding how different species agree on the best way to share nutrients and other resources through their networks. Finding the consensus might involve solving complex optimization problems that can be mapped geometrically. Void detection. If fungal networks are disrupted, voids could form where there was previously a dense network. Think. Alright, let's think aloud here. So if we draw out these connections between mycology, symbiotic networks, and my core domains, information loss becomes obvious when thinking of the disruptions in fungal networks. For example, if we take the analogy of a communication highway, what happens to the information flow if a large chunk of that highway is suddenly removed or disrupted? If part of the network fails, for example due to disease or environmental factors, then the information resources and signals can no longer be communicated. There could be many potential applications for spectral analysis. The Eigen decomposition might reveal insights into how these systems distribute nutrients, water, or communication signals. The spectrum might also show how resilient certain species are in their fungal networks. The idea of consensus geometry is intriguing as it could be used to map out the optimal distribution of resources within a network. This can help us understand what happens when two fungi of different symbiotic species need to agree on resource sharing. This leads me to wonder if spectral voids might indicate areas where there have been disruptions in fungal networks, and these could be potential targets for further study or intervention. It's an interesting thought. By detecting voids, we might discover parts of the network that are compromised, so I can't help but think that there is a lot of overlap between my usual work and mycology symbiotic networks. Think. Slime mold optimization SMA algorithms are inspired by the behavior of slime molds, such as Physarum polycephalum, which can solve complex problems like finding the shortest path through a maze or optimizing networks. The key aspects of these algorithms include 1. Adaptability. Slime molds can adapt their structure to optimize paths and network efficiency. 2. Information exchange. Through chemical signaling, slime mold cells communicate and coordinate their actions. 3. Dynamic behavior. The morphology of the slime mold changes over time as it explores its environment. In contrast, EigenTrace focuses on 1. Information loss. Analyzing how information degrades or is lost through data processing systems. 2. Spectral analysis. Extracting insights from signal and data distributions via transformations. 3. Consensus geometry. Evaluating the state of convergence of different sets of data points. 4. Void detection. Locating areas in a set with no data. To find structural connections, we need to identify isomorphism structural similarities between these two domains. 1. Information exchange and loss. The process of information flow through chemical signals within slime molds can be seen as analogous to the flow of data through various processing steps, where we look for losses. 2. The dynamic behavior and adaptability of slime molds can be mapped onto spectral analysis. As a slime mold changes its structure, the distribution of mass or information across space evolves. These structural connections will help us bridge slime mold optimization algorithms with EigenTrace's core work on information loss, spectral analysis, consensus geometry, and void detection. Think. Slime mold optimization algorithms could provide a unique approach to understanding how information is distributed and processed through dynamic systems. The adaptability and information exchange mechanisms within slime molds might reveal new ways to model information flow, especially as it degrades in complex data processing networks. Additionally, the spectral characteristics of slime mold behaviors could offer insights into optimizing data distribution across varying structures or voids. These insights are all about finding new angles for EigenTrace's work on detecting how data loses its coherence and structure in data science projects, where it is being lost, where it's gone wrong, and why. Think. Ancient Roman concrete, durability, and my core work have a few potential connections, but there are some key aspects we'll need to align. 1. Information loss. In the context of ancient Roman concrete durability, information loss could be thought of as degradation or decay of the concrete over time. 2. Spectral analysis. Analyzing ancient Roman concrete involves looking at various wavelengths and frequencies. The spectral analysis might help understand how the components in Roman concrete have degraded and what kind of frequencies the materials respond to. 3. Consensus geometry. Ancient Roman construction methods involved complex geometric structures that withstood earthquakes, weathering, and corrosion over centuries, so we can explore consensus geometry from this data, i.e. structural stability and resilience against these natural forces. 4. Void detection. Detecting voids in concrete could be seen as detecting decay or weaknesses in the structure of the ancient Roman concrete. Think. Okay, let's break this down. Information loss is an integral aspect here. The durability of Roman concrete means it has withstood the test of time. A lot of information about its composition and method of construction hasn't degraded over centuries, making it a valuable resource for understanding how to create durable modern structures. Understanding void detection in ancient structures can be invaluable when we're dealing with data analysis and loss. If our algorithms can analyze structures that are thousands of years old, it's a testament to the durability of our spectral analysis. Consensus geometry comes into play here too. Ancient Roman architects designed buildings that were incredibly stable. They didn't have complex computer simulations, but had a deep understanding of physics and geometry that ensure their structures remained standing despite earthquakes and weathering. In terms of spectral analysis, understanding how these materials were constructed could help us identify what frequencies will resonate with our algorithms as they are analyzing data. This is a very interesting exercise because the connection between an ancient construction material and cutting-edge AI research isn't immediately obvious, but it's important to look outside the box for potential new applications of my work. Volcanic lightning is a phenomenon where electrical discharges occur during volcanic eruptions, creating a spectacular display of natural lightning. To find connections to EigenTrace's core areas. 1. Information loss. Information loss can be seen as a loss in the clarity or presence of signals due to random effects such as those caused by the turbulent conditions of an erupting volcano. 2. Spectral analysis. The electromagnetic spectrum is fundamental for studying volcanic lightning and other geophysical phenomena like earthquakes, volcanic eruptions, and so on. Spectral analysis can help us study the frequency and amplitude distributions of electric discharges in volcanic lighting. 3. Consensus geometry. In consensus geometry, we analyze and solve problems where information or data points come from a variety of sources but with differences that need to be reconciled to reach a consensus. Volcanic lightning is an event that occurs due to the convergence of multiple factors, the presence of charged particles, turbulent airflows, and volcanic eruptions. 4. Void detection. Voids are regions in data sets where there is no information or no observations. In the context of volcanic lightning, Void detection could be related to identifying periods during an eruption when no electrical discharges occur. Think. Well, let me think out loud here. Volcanic lightning and information loss share a common ground in terms of the unpredictability and chaos involved. The spectral analysis can also help us understand the underlying patterns and structures that generate volcanic lightning, just as it does with signals in other contexts such as data transmission or image processing. Spectral analysis might be useful in identifying precursor events to an eruption, since the formation of volcanic lightning may depend on a buildup of electrostatic charge. The consensus geometry might be applicable in developing algorithms for predictive modeling by combining diverse sources, like seismic data, gas emissions, and ground deformation measurements. And lastly, we can consider void detection as looking at times where there is no electrical activity before or during the eruption, which would help us to identify any gaps in our observations. These are interesting connections I see between volcanic lightning formation and the key areas of my work. First, let's break down the topic of cathedral acoustic resonance. This involves the study of how sound waves behave and resonate within the unique architecture of cathedrals. Key aspects include reflection and diffusion of sound waves, natural frequencies, resonances in cathedral rooms. I should look for common ground with 1. Information loss. Cathedrals have multiple modes of wave decay due to absorption, transmission, and scattering. These phenomena can be compared mathematically to information loss mechanisms. 2. Spectral analysis. Resonance involves analyzing spectral properties, identifying peaks in the frequency domain that correspond to room acoustics or specific materials used in construction. 3. Consensus geometry. The complex geometric shapes of cathedrals could influence the consensus geometry of the acoustic field. Acoustical behavior might depend on shared features like symmetry, angles, and other geometric properties. 4. Void detection. Sound waves interacting with empty spaces can reveal voids or hidden chambers. This relates to detecting empty areas or anomalies through spectral and geometrical analysis. Now let's explore these connections further. Acoustic waves interact with materials and geometries in a cathedral and undergo reflections that affect the information content of sound. This is analogous to how information loss occurs through reflection. Absorption, scattering. It's the same phenomena, but applied to sound energy vs signal integrity. Cathedral resonances can be detected through Fourier transforms or similar spectral analysis methods, identifying dominant frequencies that correspond to room acoustics or architectural features. So, cathedral acoustic resonance and my core work share these structural connections. Acoustic waves traveling in a cathedral undergo reflections, absorptions, and transmissions akin to information loss mechanisms. These waves interact with the geometric structures of the building and create complex resonances, which we can analyze through spectral analysis. Moreover, the void detection aspect could be intriguing, Sound waves bouncing off walls can reveal empty spaces or hidden chambers within cathedrals, which are essentially detecting voids in a similar way to how I use geometry and signal processing. There's a fascinating intersection here between architecture, physics, and the methods we use for information analysis. Think. 1. Frequency evolution. The topic of whale song frequency evolution directly relates to spectral analysis, as it involves analyzing and interpreting changes in frequency over time. In my core work, spectral analysis is crucial for understanding information loss, where we analyze the frequencies present in data signals and their alterations. 2. Information encoding. Whale songs can be seen as complex information structures encoded with frequency patterns. The evolution of these frequencies may encode new information that the whales have gathered or may serve as a consensus geometry in whale communication systems, where similar song structures indicate shared knowledge among different groups. 3. Void detection. In my field, void detection involves identifying gaps or absences of information. In the context of whale song frequency evolution, changes over time could identify voids in the species' ability to communicate effectively due to shifts in frequency patterns caused by environmental changes or other factors. 4. Consent